Hello, chemistry students. Today we're going to be talking about intermolecular forces. Now, intermolecular forces are the attraction between different molecules. This is often confused with an intramolecular force, which means a force within a single molecule. Those would be examples of chemical bonds. So if I look at an example like H2O, the bonds connecting the H's and the O's are intramolecular forces, chemical bonds within the molecule. What we're looking at today are intermolecular forces. This is the attraction of one water molecule to a totally separate water molecule. Now, it's not a bond, it's just a force of attraction. Now, typically when we talk about intermolecular forces, we're going to be comparing covalent molecules. Those are molecules made up of only nonmetals. If you ever see an ionic molecule, something that contains a metal and a nonmetal. Now, these are typically held together using Coulomb's law. We're talking about attraction based on the size of the atoms and the size of the charge. Ionic are going to be stronger than the remaining covalent attractions. So if you ever see an ionic compound, we're typically just going to rank that one as the strongest intermolecular force, the greatest attraction. And then we'll compare the three covalent ones: hydrogen bonding, dipole-dipole, and London dispersion. Now, among those three, hydrogen bonding is the strongest. This exists when you have a hydrogen atom, and it has to be bonded specifically to fluorine, oxygen, or nitrogen. Now, it has to only be those three, and it has to do with the size of the atoms and their size of their electronegativity difference, but it can only be those three, and it also has to be a polar molecule. So if a molecule meets both of these criteria, it would have hydrogen bonding, where the hydrogen of one atom can attract the F, O, or N of a separate atom. Dipole-dipole forces are the next strongest. This occurs if a molecule is polar. So a molecule that has hydrogen bonding would also have dipole-dipole because it meets the criteria of being polar. So this is a polar spell molecule correctly here. Polar molecule. London dispersion are the weakest. These exist in all molecules. For our purposes, we're going to be considering any nonpolar molecule. This would be the strongest type of force that it would have. London dispersion forces have to do with just having electrons. The more electrons a molecule has, the stronger its London dispersion forces are. Now, I have these ranked from strongest to weakest. There's going to be some overlap between these, so it's not exactly a strict criteria. You could have London dispersion forces that are stronger than dipole-dipole, but that gets a little bit more complicated. This is just a broad overview of comparison. Now, if I want to think about how this actually looks in real life, I could consider two different molecules, and we already kind of looked at H2O in that little picture above. If I have a water molecule, I have a single oxygen connected to two separate hydrogens. Now, when I look at that bond, an oxygen has an electronegativity of a 3.5, and a hydrogen has an electronegativity of 2.1. So when I look at the difference between those two electronegativities, it's a polar bond, and the oxygen is going to be the one pulling the electrons towards itself. That creates an unequal distribution, making it polar, which means that the oxygen is going to pull the electron density towards itself, making it a partial negative end. The hydrogen would then be left as a partial positive end. So we get a polarity pointing towards the oxygen in a water molecule. Now, when I think about ranking this in terms of IMFs, I see that it's polar. I also know that it has a hydrogen bonded to an oxygen, which is the second criteria. So I know that water would have hydrogen bonding. If I were to sketch this, I would draw two separate water molecules. For any example where we're looking at intermolecular forces, you need at least two of the molecules for comparison. I've drawn the bonds as straight lines, and if I wanted to draw the intermolecular force, this would be a dotted line connecting one of the oxygens to one of the hydrogens. They're from two different molecules, so this would be my hydrogen bond. That unequal distribution creates these partial negative and partial positive charges, which are going to be this electrostatic attraction. The partial positive of one hydrogen is going to attract the partial negative of another oxygen. So the hydrogen bond is between those two molecules. Now, if I look at something like HCl also has a polar bond. We said hydrogen has an electronegativity of 2.1. Chlorine, has an electronegativity of 3.0. Chlorine's going to pull those electrons towards itself. Chlorine's going to be the partial negative end. Hydrogen's going to be the partial positive end. I have a polar molecule again, but the difference is I do not have a hydrogen connected to an F, an O, or an N. So I would not have hydrogen bonding. In this case, I'm going to draw two separate molecules. I'm going to have my HCl, and it's going to be attracted to another HCl, where the partial negative chlorine is going to be attracted to the partial positive hydrogen of another molecule. Now, this would be a dipole-dipole interaction. Dipole meaning two poles, a positive pole and a negative pole. So two differently charged atoms are going to be attracted. So these are the attractions between the molecules. Now, there's a handy flowchart that you can use to quickly figure out what types of IMFs a molecule is going to have. If it's a polar molecule, you automatically know that it's going to be either hydrogen bonding or dipole-dipole. If it's a nonpolar molecule, your only option is London dispersion. So that's an easy first step to take. If you see that hydrogen bonded to an F, an O, or an N, that then qualifies it as hydrogen bonding, and if not, then it's just dipole-dipole. So let's just look at a bunch of examples here and just practice. I see N2. That's a nitrogen triple bonded to itself. If I were to draw my Lewis dot structure, typically that's the first step in drawing any of these. You want to see what the shape actually is. Any two atoms bonded to itself, there's going to be zero difference in their electronegativity. That's going to give me a nonpolar covalent bond and a nonpolar molecule. Well, what's the only type of IMF that nonpolar molecules can have? London dispersion forces. So N2 would only have LDF. Carbon monoxide, however, has a carbon triple bonded to an oxygen. And again, we would normally take more time to draw out these Lewis dot structures. I'm just sketching them out pretty quickly here just to save us a little bit of time. Now, this bond will be a polar bond. Carbon is 2.5, oxygen's 3.5. So that bond is going to be pulling towards the oxygen. This is a polar covalent bond, which means I'm going to have a polar molecule. Now, I don't have a hydrogen in this molecule, so I don't have hydrogen bonding. So my strongest bond would be dipole-dipole, or intermolecular force would be dipole-dipole. HF, this is similar to the HCl that we looked at on the previous page. Hydrogen's a 2.1, fluorine's a 4.0. I've got that polar covalent bond. It gives me a polar molecule, but I also have a hydrogen bonded to an F. So this one's going to have hydrogen bonding. NaCl should jump out at me right away. Whenever I see that sodium, I'm not going to be thinking about a normal Lewis structure here. I'm going to be thinking about drawing brackets with my valence electrons here. I'm going to draw it in this format. This is an ionic format, an ionic formula. So right away, this is going to have an ionic IMF. It's going to have a pretty strong attraction between those sodium and chloride ions. And again, I would be using Coulomb's law to describe that attraction. As we get to some more complicated shapes, we have to start taking into account the 3D structure. In something like methane, CH4, I'm going to have a tetrahedral shape. I'm going to have 4 hydrogens all equally distributed around that central carbon. Now, when I do that, each of those bonds is a polar covalent bond, but because all of them are equally dispersed around that central carbon, it's going to be a nonpolar molecule. Well, that means my only option is going to be LDF. So even though I have polar bonds, I have to take into account the 3D geometry of that molecule. Now, methane is a symmetrical molecule where all of the atoms around the central atom are identical. If I change some of those hydrogens into chlorines, well, now I'm going to get a different answer here. This is also going to be a tetrahedral molecule, but now I'm going to have 2 hydrogens and 2 chlorines. Well, now it's no longer symmetrical. It's going to be this kind of offset shape here, where the chlorines are going to be attracting the electrons towards themselves. They have a greater electronegativity at 3.0 compared to the carbon at 2.5 compared to the hydrogen at 2.1. So I'm going to have my arrows pointing in towards the carbon from my hydrogens and then away. So this gives me kind of a offset polarity here, where it's going to be shifted towards the chlorines, however I orientate my molecule, or the chlorines are going to be my partial positive, or excuse me, partial negative, and my hydrogens would be my partial positive end. Now, this has polar covalent bonds. It's a polar molecule, but I do not have a hydrogen connected directly to an F, an O, or an N. So this would still be a dipole-dipole IMF. A little bit harder though. I have to think 3D in these ones. Makes it a little bit tougher than just a two-atom molecule. Now my last one here, ammonia. I've got a nitrogen bonded to 3 hydrogens. That nitrogen has a lone pair on it. Whenever we see a lone pair on a central atom, we know it's automatically going to be a polar molecule. In this case, nitrogen has an electronegativity of 3.0, hydrogen's 2.1, so my electron density is going to be pulled towards the nitrogen, which means that the nitrogen is going to be my partial negative, and my hydrogens would be my partial positive end. These have polar covalent bonds. It's a polar molecule. And then I asked myself, does it have a hydrogen bonded to an F, an O, or an N? And it does. So this one would have hydrogen bonding, where the hydrogen of one of these molecules would be attracted to the nitrogen of a different ammonia molecule. Hopefully this helped looking at a few examples of classifying intermolecular forces, ranking them by strength. We're going to look at properties of intermolecular forces and how they change the properties of a molecule in a future lesson. Hopefully you found this helpful. Thanks for tuning in.